Now, let's look at the first part. So in question 5a, it says write fx in the form of a times x plus b squared plus c, where each of these letters are integers to be found, okay? And you also got parts b and c. Now, let's just focus on part a for a second. Now, to rewrite this function in this form, we first have to notice that this form is known as completing the square, yeah? So let's go ahead and underline the function. Now, the objective to completing the square is that we always need to firstly rewrite this in just x squared form. So we gotta get rid of that 2. And to kind of get rid of 2, we need to factor it out. So look a bit like that. If you factorize 2 out, you just divide 2 across, so you got x squared plus 2x plus, well, half of 9 is 4.5. And now to officially complete the square, the key idea is to underline these two terms, x squared and 2x, and then half this coefficient of 2, yeah, and then wrap it in a bracket. So it looks a bit like that. You got x plus 1 squared wrapped in a bracket, then you copy next term, then you subtract the thing you squared by, well, squared. So it'd be minus 1 squared. And we're pretty much like done here, guys. So all you have to do now is, instead of multiplying this out like completely, because notice how they got a little a outside x plus b, they literally stuck this 2 on this bracket, but then they left the next part as one whole number. So what we can do here is literally partition this. You got 2 of that and 2 of the next set of terms, and then you just say, okay, what is 2 times all of this? So just smash this in your calculator, guys, and you should get a 7 for that one, and therefore your final solution is going to be this, where A, B, and C have been found. And that's it, like nothing to it. Now moving on to part B, so we're going to shift this up there. It says sketch the curve of equation y equals fx. Alright, so sketching. Sketching is kind of easy, like so depending on what you're trying to find. Showing any points of intersection with the coordinate axes and the coordinates of any turning point. Now one key thing, guys, yeah, is that when you got an equation like this, the turning point is actually found from here. The turning point in this case would be like when this part equals 0. So in other words, x needs to be minus 1. And if x is minus 1, because it's all 0, you're left with a 7. But let's do it step by step. So we say, alright, to find any turning point, first things first, we need to define it, yep? So let that equal to 0, you get x equals minus 1, just like we said. And then, obviously when x is minus 1, this cancels out and you just get a 7. Perfect. Now, because they want to sketch this curve, we're just going to whip out an axis like this. And the key idea, guys, is to firstly plot this turning point. So notice how we got minus 1 and 7. So what I'll do, I'll go minus 1 across, and then go up by 7. So I'll put it over here. So in this case, I'm going on blocks of 2's. Now, because we know what minus 1 and 7 is, we can plot like a little curve like that, and this would be where the turning point is going to lie. This is the coordinate where it's marked. Now, another thing is, guys, is because they also want us to show like any points of intersection. In this case, your only point of intersection is going to be over here at the y-axis. And we need to remember, when something hits the y-axis, we know that x equals 0. So I would go ahead and use this original equation here, replace x with 0, just like we did here. And again, you can call this y if you like, because that's what fx is. Fx is literally y. And we replace x with 0, just go ahead and smash in the calculator, you're going to get a 9. And that's it, guys. That's part B done. Now, moving on to the next part, which is part C. It says, describe fully the transformation that maps the curve with equation y equals fx onto the curve with equation gx. Alright, so this is kind of a little straight up mapping here, replacing one with the other. So here is our gx function. We're going to come to this one in a second, yeah? Now, looking at gx for a second and then looking at fx, we just got to spot what's going on. Like, they don't actually tell you what's going on, we have to actually see it. Now, it's not very clear what's happening at the end, but in the beginning, you can kind of see how they replace this 2x squared with 2 times x minus 2 all squared. That literally tells us that x has been replaced with x minus 2. Now the question is, why hasn't this one got x minus 2? Well, that's because they probably already expanded it and then added some kind of constant and got minus 3. Now to do that, guys, I would literally write this. I'll say, alright, knowing the fact that gx is kind of related to fx, we can say let gx equals the function of the function of f itself, replace every single x with x minus 2, and then add some constant k, because maybe there might be some kind of extra values, we don't know. So let's do it. Let's go to update this function f with x minus 2. That means all the x's look like that now. 2 times x minus 2 squared plus 4 times x minus 2 plus 9, and also the plus k which added. Okay, now what can we do here? Notice on the last bit you got 4x minus 3, yeah? So let's just go ahead and expand the right hand side, yeah? Leave the left hand side alone. So on the right we got 4x minus 8 plus 9 plus k. Tidying up this bit, so minus 8 plus 9 will give us 1. So in the end we have k plus 1. And now matching up terms, you can see that everything looks kind of the same. The only difference is now is that you got -3 here and a k plus 1. So I'll go ahead and say, okay, this must mean that k plus 1 has to be -3. Take away 1 across, you should get -4. And that's it, guys. We essentially have a transformation now. Like if you look in the beginning, it said gx equals f x minus 2 plus k, okay? We know that this function tells us there's a shift. Now because x minus 2 is going to be shift on the right, and plus k means it's going to be up or down shift. Because k is -4, it's going to be a downward shift. So in other words, it's going to be translation of 2 across to the right, positive, and 4 down. Or in other words, it's going to look like a vector like that. Okay, so this is your vector transformation. 2 across and 4 down. And yeah, that's CI done. Now for the last bit, for part 2 of that question C, it says find the range of this function. Okay, when it comes to ranges, guys, ranges deals with heights, yeah, like how far it goes, like the minimum and the maximum, to generalize it. So we need to find either a maximum or a minimum. Now looking back at this function, this is function h. We've got 21 over this. This little bottom bit is fx. That means I could go ahead and say that this function equals 21 over fx. Now, because we're dealing with like maximum and minimum, I would use the turning point, because if you remember from the previous question, we had a graph and it told us some kind of, it was a U-shaped graph, and then we had a turning point. This is going to be used here again. So let's go ahead and replace fx with that turning point equation, yeah? Now, this is going to tell us a few things, okay? We know firstly that the turning point was at x equals -1. What happens if we replace this -1? Let's just check it out. This is what we get, yeah? If x is -1, put this in the calculator, this is 0. You're just left with 21 over 7. And simplifying that, you get 3. Okay, so this 3 is going to either represent the maximum shape of the curve or the minimum. So this is going to be your highest or lowest value. So how do you know which one's going to be? Well, what I will do is that I'll get a table of values here, and I'll just plug in like a bunch of positive values. Okay, I'll just go ahead and just plug in. And if you plug into the equation, you'll notice that, I don't know, from 0 to 100, it's kind of decreasing here. Like you get 2.33, 1.4, and so on. So far we know the highest is 3, but it seems to be going down towards 0. It doesn't seem to dip below 0. And the reason why, because if you realize, if you plug in any negative value here, just for instance, yeah, and you square it, it'll be positive. That's why if we did another table of negative values, you'll notice that when x is -1, again, you get 3, which is the highest it can be. And if you plug in any other value, like between like -100 or +100, you're just going to get a bunch of positive answers between 0 and 3. And that's it, guys. That's your range. Your range is literally capped between 0 and 3. I don't know how the curve actually looks like, but we don't have to plot that. And if we write the answer, we can say that the range is a function of h between 0 and 3, except that it includes 3 and it doesn't include 0. So, number 6. Solve for theta between -180 and +180, the equation below, giving your answers where necessary to one decimal place. And there's also a part B too. Now, to deal with a question like this, my advice, guys, is to firstly understand what do we want to achieve here. Yeah? Well, the objective usually, guys, is to either like solve these kind of trig equations in either sines or coses. Yeah. The reason why is because those two are closely related, and they're the easiest to reduce things to. Now, let's have a look. Sine 2 theta is known as a double angle trig identity, and double angle trig identity tells us that this is supposed to equal 2 times the regular sine theta times cos theta. And tan theta is also another identity. Tan theta itself is equal to sine over cos. Okay. Now, what we're going to do, we're going to substitute both of these into the equation, so it's going to look a bit like that. You're going to get 5 times what you just got and 9 times the second identity. And luckily, you know, on the first side, 5 times 2 is 10, and 9 times that is just, well, just stick it together. So you get something like that. Now to tidy this up, my advice for any single question that has fractions is to clear the fraction. So let's multiply cos theta across. So if you multiply cos across, you're going to get, what's it called? You're going to get 10 sine theta times cos squared theta, okay? So just stick these together. And then at this case, I mean, I would say -9 sine theta across. You could, but we need to firstly try and make all of this in terms of one identity. In this case, we're going to make it in terms of sine. Why? It's because cos squared theta alone is actually another identity. Well, it's actually part of an identity. It's part of the sine squared plus cos squared equals 1. And this identity can be rearranged to make cos squared theta a subject. So you get 1 minus sine squared theta. So let's go ahead and substitute all of this thing into this equation. And if you do that, you get that. 1 minus sine squared theta equals 9 sine theta. So almost done. Almost done. Now at this stage, I'm going to just line this up. At this stage, I'm going to go ahead and expand this, and you're going to get 10 sine theta minus 10 sine cube theta, because sine theta times sine squared is sine cubed. You also get 9 sine theta. Lastly, we'll now collect like terms. And now, and then if you rearrange this, you can subtract 9 sine theta across with 10 sine theta to get 1 loss of sine theta, and then minus 10 sine cube theta. And guys, be careful with this step here. Whatever you do, don't move this other side, because if you start cancelling terms out, you actually ruin the answer. Instead, we need to factorize sine theta out both of them. And if you do that, you just can get 1 on the left, and you're gonna be left with a 10 sine squared on the right. And that's it, guys. So let's just pull this across to a fresh page, yeah? So from here, what do we do this? Well, it tells us that this times this bracket gives you 0, meaning just like a normal quadratic equation, you have two solutions. Sine theta equals 0, and also the term in the bracket equals 0. Except you can rearrange this and make sine theta the subject. You can, subtract 1, divide by minus 10, so you get a tenth, and then square root answer, so you get plus minus the square root of 1/10. Okay, great. Now, what can we do from here? So at this stage, the purpose of this question is to find all the solutions of theta, right? So let's go take sine theta equals 0. If we rearrange this to get the sine inverse, well, the sine inverse of 0 is 0 degrees. And yeah, we do the same for the second part. You got sine theta equals plus minus root 1 over 10. Well, let's look at the positive. If we sine inverse the positive solution, you get 18.4. And if you sine inverse the negative solution, you get minus 18.4. Okay. So when you get all three solutions, this is actually not the end of the question, because there's actually a bunch of other solutions that we ain't seen yet. And the reason why we know this is because in the question it said find all solutions between minus 180 and plus 180. So far we've only got a few in the middle. We ain't even got the endpoints. Well, to get endpoints, all we need to do is firstly draw the sine graph, yeah? And if you remember correctly, guys, a sine wave looks like this. So from minus 180 all the way across, this is what we have. The endpoint says plus 180, and the left endpoint is minus 180 degrees. Okay. Now, to get all the solutions, this is what I would personally do. I would take this value we just found, which is plus root 1 over 10. And this is kind of a straight line that cuts through the y-axis. So if you draw a straight line of this value here, so just make it somewhere above, it'll look a bit like this. And it'll hit at 2 points. One over here and one over here. Now, if we think about it carefully, guys, we just think about it. We know that the first point here must be 18.4 degrees, yeah? Because that's what we got. And there's another one here. And if you look at it, this is 18.4 degrees away from 0. Because the sine wave is symmetrical about its peak, so in other words, in the middle, it's like literally bang in the center at 90. That means over here is just close to 180. So we've actually got a value which is 18.4 degrees off 180. So we can kind of subtract it. And before we do that, we can kind of do the same for the negative version. So just draw a line across and hit at 2 points, and we get more or less the same result. We know that this very first point close to 0 is minus 18.4, and this is kind of in the same position as it was above here. So this is 180, 18.4 off 180 on the negative scale. So essentially, in your calculator, if you just write 180 take away 18.4, you're going to get a plus minus solution of 161.6. Makes sense. So that's actually your two endpoints. Now, we have to be careful not to forget one other value. That's 0. Because if you look at this 0 here, this means that it crosses the y-axis at the origin. In other words, you're looking at the x-axis. So we can just say that these 3 points is where the curve hits the x-axis. So at these endpoints, we know one of them is 0, and the two endpoints must be plus minus 180 degrees. Okay? And oh yeah, it's good to summarize all your results. So because they want one decimal place, we can write 0.0 and plus minus 18.4. And that's it, guys. That's this part done. Now, let's go ahead and look at part B. So deduce the smallest positive solution of this equation. Okay, so this is not so obvious here, but if you remember from part A, this is the exact same equation as what we're given. The only difference is that this part was 2 theta, and this bracket was just theta. So if you think about it, we could say that x minus 25 is actually theta. And this is kind of following on from part A. So we kind of have to use all the angles we had previously to resolve this. Now, when it says find the smallest positive solution, it means find x, yeah? So if we add 25 across, we want to find a solution that says theta plus 25, but the smallest x value you can get. So let's just whip out the previous solutions, yeah? This is what we had earlier. Now, if we think about it, we can't use these massive values. Like we can't use the positive values because it will be a huge x value. We can't use the negative values because you'll still be negative. 0 is kind of useless for the same reason. Well, not useless, but it can be, right? However, 18.4 isn't so bad. If you plug in plus 18.4, well, you're going to get a big value. But if you plug in minus 18.4 and add 25, you're going to get a value just bigger than 0, which is actually 6.6. And yeah, guys, that's literally all you do for part B. Now, 7. It says in a simple model, the value, be pounds, of a car depends on its age t in years. Alright? The following information is available for car A. Now, it says that its value when the car is new is 20k. And the value after a single year, it means it dropped by 4k, it's 16k. Now, use an exponential model to form for car A a possible equation linking V with t. Alright, so let's just ignore the other two parts here. Now, what it's trying to say here is that we just need to pull out an exponential model. Well, the exponential model is always the same, yeah? It's always going to be V equals some random constant, like the value of the car, for example, and how much is either exponentially increasing by or decaying by. Well, when we deal with cars in real life, you know the value is always tipping or dropping every single year. The first year is always a massive drop, and then it suddenly like kind of slows down. That's kind of what this equation represents. It's the decaying equation. Now, let's have a look at the bullet points. It said in the beginning that its value when it's new is 20k. So this means at time 0, because remember we're working with time t here. At time 0, like immediately after you got it, the car is 20k. So we have a value of the car equals a equals e times k to the power 0. Remember, so all you do is replace v of 20k, the value, and time, which is how long it's been, with 0. Now, simplifying this equation ain't so bad. We need to recognize that k times 0 is 0, e to the power 0, or anything to the power 0, guys, is 1. So we're just left with a times 1, which is 1. So this means that 20,000 equals a. And that's it, guys. We got our a. Now, the second bullet point tells us that its value after 1 year is 16k. This means car after 1 year, t equals 1. So it's been a single year. So we're going to go ahead and use, in this case, the v equation again. But we're going to update this a value 20k and replace v here with 16k. And of course, t itself is 1. So this is what we got. Now, the purpose of this, guys, is to literally find the value a and k, right? We found a. Let's go ahead and rearrange to find k. So what I will do, I'll go ahead and drop 20k across. So we've got 16k over 20k, which is 4/5. E to the power of that is still ek. Okay. And to find the value k, we need to get rid of the e. And to get rid of the e, we need to take the natural log. So take ln on both sides. If you take ln on the left, well, you leave it like that. If you take ln on the right, well, ln and e cancel out. So then you just get k. And that's it, guys. That's your value k. But they don't tell you how they want it. So because they don't tell you, you could leave an exact form. Or, if it helps, I would round up a bit. I would leave it in decimal form. So therefore, k equals negative 0.223. And the reason why this is looking right is because we know that the value car is dropping. And because there's a negative in front, it means it will be dropping. If it was positive, that means the value will actually go up, which is kind of messed up because it only works with antique cars. And yeah, so this should be okay. So putting everything in, replacing your a and your k into the original v equation, you should get a general valuation of a car in this form. And this should cover part A. Now, let's follow that with part B. Yeah? It says that the value of car A is monitored over a 10-year period. Its value after 10 years is 2k. Evaluate the reliability of your model in light of this information. Okay, so they kind of want some kind of description afterwards. Now, first things first, we know that the value after 10 years is 2k. But before we do that, let's go ahead and replace t with 10 and see what happens, yeah? So we can say after 10 years, the value is going to look like that. It'll be 20k times that. Busting this in your calculator, you should get an approximation of 2,150 pounds. Now, the reason why this is reliable is because if you take this to one significant figure, you'll get 2,000. And that's really it. This is why the model is reliable. Yet you have an answer which is approximately similar to whatever system they're following. And that's cool. That's what you need to do. Now, let's look at the final part of this question. It says that the following information is available for car B. So we've got another car with different specs. It has the same value when new as car A, so they both start at 20,000. Its value depreciates more slowly than our car A. So that means the decaying factor is a bit less, well, closer to 0. Explain how you would adapt the equation found in part A so that it could be used to model the value of car B. Alright, so 1 marker. So it's literally what we were just saying. We just look at the bullet points. So because we know it has the same value as car A, this means that when a car is new, it has the same value. So for car B, for the coefficient of A using the original equation, it's also 20k. However, because it depreciates more slowly, we say this. We say that the exponential decaying factor, in other words, the negative power on E, will be less negative or closer to 0. This means that instead of like minus 0.2, it could be like minus 0.1 or minus 0.05, but not at 0, but between those two ranges, between this value and 0.
I just want to thank you guys for coming to this end of my channel, and if you've enjoyed the content so far, just go onto my channel page, hit the subscribe button and hit the bell for more notifications, and if you want, you can do personalized or all, and that way you won't miss any future maths or educational videos. Anyway guys, thank you for watching and see you next time. Ciao.